Hello? Okay, I'm on. That's great. Hi, my name is John Lee. I run the cluster products inside Cray. So Cray acquired a company called Appro. That's the company that I'm from back in 2012 and added the cluster product line to their overall product portfolio. My colleague, Maria Yordake, is our product management director in charge of our CS Storm product, which is a product that we're going to be talking to all of you guys today. Our lawyers made us put this up there, so let's go to the next slide. Today, we're just going to be talking about a few things. We kept the agenda fairly simple. I want to tell you a little bit about Cray. Since you guys are on the HPC track, you guys probably know who Cray is, but Cray has gone through many iterations throughout its life. So I wanted to take you back to history a little bit and tell you guys what's been happening inside Cray. And I'm going to be focusing primarily on the platform, on the hardware. Okay, I'm a hardware geek. I like talking about hardware. I love speeds and feeds. So that's the stuff I'm going to be talking about, why we made this product, why we think this is the best GPU platform for you. And Maria's going to be talking about what you do with that platform. Okay, and she's going to be talking about how you're able to scale GPUs in our CS Storm product. Our CS Storm product is a single server that can hold up to 8 physical GPUs. It's a very, very powerful system. But at the same time, as you guys know, it's not easy programming on GPUs, let alone 8 GPUs inside of a single host. So she's going to be talking about some of the experiences that we've gained doing that. Okay? So let's talk about Cray, right? So Cray has gone through many iterations in its life. I think we've had more, we've reinvented ourselves more often than Madonna, right? So Seymour Cray started Cray back in the 1970s. Really, Cray is synonymous with supercomputing. It's a fantastic brand inside high-performance computing. But it went through some more difficult times. It was acquired by SGI back in 1996. Inside Cray, they referred to that as the dark period, I believe, is what they referred to that period as. But since then, Cray has really revitalized. In fact, the analysts are talking about Cray. Cray stock obviously has been doing very well, but also financially and from a corporation perspective, Cray has been on an incredible rise the last several years. We have a little over 1,000 employees, and we're adding like 200 employees every year. So Cray is growing, and that's fantastic for high-performance computing because Cray is one of the few companies that is investing significantly back into high-performance computing when many of the other companies have not been. So that's actually very, very good for high-performance computing. We're not a single-trick pony anymore. Okay? We not only have a high-end MPP machines, but we also added clusters, we've added storage, and we have analytics products. So we have 3 focus areas in the areas of compute, storage, and analyze. And we have many development sites. Maria and I come from the San Jose office, which is primarily centered around our cluster products, but in Pleasanton, just across the bay, is where our analytics products are located as well. Okay. So our high-view vision of Cray. So when you think of Cray, you think of our monolithic, very large systems. When we look at the world, what we want to do is we want to provide tools for you, our customers, to be able to do fantastic things with those tools, and really give you the ability to be able to model the entire world. So on the left-hand side, on the compute side, this is the classic Cray, taking very complex computations and providing solutions where you'll be able to do that work very well. On the right-hand side is where we see a tremendous growth coming in, where you see this explosion of data and ability for our customers to be able to make usage of that data somehow, and then combining the math models and the data models to provide our customers the ability to really make something useful out of that data. So when you think about Cray, you're really thinking about supercomputers, and we can now say that we are number 1. So if you take a look at the last top 500, the top 50, the top 10%, we currently have the most number of systems, and we're also tied with IBM on the top 100 as well. So we're very proud of that. Let's talk specifically about GPUs. We're at GTC, so we're talking about GPUs. The pie chart that you see over there shows that Cray has more GPU systems in the top 500 than anyone else. In terms of overall aggregate performance on GPUs, Cray has more than every other company combined. What that means is that if you have a GPU computing needs, then we are the experts. The CS Storm product, the product that I'm going to be talking to you about today, is currently the number 10 on the top 500. And also, not only that, even though it's a very power-hungry machine, it's also a green machine as well. We're also listed as a number 4 on the green 500 as well. Okay, so let's talk a little bit about, give you a little background on CS Storm, why we did this product. As is typical for Cray, sometimes we do custom engineering efforts. Our customers have very complex problems, and they come to Cray and ask us to solve them. So one of our a particular customer came back and said, you know, we want to build the best GPU system that's available. We want to build the best possible GPU system. But what they're finding out in the market is that it's very difficult to get a very reliable and a system that's dense enough to be able to satisfy their needs. So they funded us to build this system. What they wanted to do was they wanted to build the most powerful GPU system available in the market today. They wanted to be able to populate 8 GPUs and be able to drive them at the maximum peak powers. At the time, I think the power envelope for the GPUs was about 235 watts per card. But they knew that in the future, NVIDIA was going to be coming out with 300-watt cards. So they said, we want to build a system that's able to cool and be able to drive reliable performance on 8 of these 300-watt GPUs. Not only that, host processor performance was pretty important for these guys. So they wanted to be able to drive the CPUs at full performance and have a large memory capacity so they could feed these GPUs as well. Okay? So what we did was we took that laundry list of requirements, went back to our engineering and said, hey, how many of these requirements can we meet? So after about a couple of weeks, these guys came back and said, hey, we can meet all of them. So from that point on, we went into an execution mode, and we delivered a production system with over 4,480 K80 GPUs. That's the system that's currently listed on the top 10. Okay? Now, this particular platform was designed to be future-proof as well. So not only does it support GPUs that NVIDIA is making today, but we will also be able to support GPUs, NVIDIA's future GPUs as well. So CS Storm, what makes this system special? Because when you take a look at just the specs, there are other platforms that can support 8 GPUs as well. But really, what we found out is that making a highly reliable production caliber GPU systems is very, very hard. Okay? Being able to drive the necessary airflow to cool these GPUs to keep them at a very low temperature operating environment is not easy. So a lot of engineering effort to do that. The second thing is, when the PCI Express bus went from a Gen 2 to Gen 3, in essence doubling the speed, making PCI Express bus reliable was also extremely hard. There was a lot of signal integrity study and a lot of engineering work that needed to happen in order to be able to drive these GPUs at their peak capacity. Okay? But we also wanted to make the GPUs serviceable as well. Okay? We wanted to give our customers the ability to be able to upgrade their system in the future. What that means is we didn't want our customers to be able to, we didn't want them to rip out the entire system just so they could replace the GPUs. And since we are building systems, not single servers, we wanted to provide a system that provided a total solution, including the power and the packaging, as well as cooling. How can we design a system that our customers will be able to do in a room-neutral design? So when you open up the top cover of our CS Storm machines, what you see is a lot of computing capacity. So on the host motherboard side, we have a 2-socket Intel motherboard that can support up to about half a terabyte or even a terabyte of memory when 64 gigabyte memory modules become available. We have room for some local drives, and right now we support SSDs. But most importantly, the star of this system are the GPUs. And we have these 2 very large carriers that are able to support 4 of these GPUs on each side. And we have GPUs on the left and GPUs on the right. This is a 2U form factor systems, and in a 48U rack, we can support about 22 nodes. So that gives you a tremendous amount of computing capacity. Okay, so let's talk a little bit about speeds and feeds and why this is important. When you're connecting GPUs to your system, you have many options. Okay? And depending on the types of applications you run, one particular connectivity may favor the other. Okay? We made a decision to have more of a balanced solution. What we found is of all the different types of applications that our customers want to run on GPUs, majority of them benefited from this architecture. Okay? Not all, but majority of them do. Okay? So what we do here is we simply take, with the Sandy Bridge processors and continuing with Ivy Bridge and Haswell, the Intel processors has the PCI Express root hub built into the processors. There are 40 PCI Express lanes that come out of that. So we take 2x16, connect it to a PCI Express switch, and then we hang 2 GPUs off of that. Okay? And then with the remaining by 8, we connect a high-speed network so that you have a locality so that you can do GPU direct to each side. So that allows for a very balanced performance between the two, between all the 8 GPUs. So another key thing that's different between the cluster product group and our MPP systems is that on the MPP side, Cray does everything. Cray develops our own motherboards, our own Aries interconnect and whatnot. On the cluster side, we tend to leverage more of the ecosystem. So with the motherboard, what we did was we went to Intel and we gave them a specific list of features that we were looking for. We co-designed 2 motherboards with Intel. One is a compute node focus motherboard. The other is a kind of a GPU host-based motherboard. So this motherboard has features that are important in a GPU host. So what are some of those things that are important? Being able to bring out all 80 lanes out of those 2 processors. It's not easy to bring all 80 lanes out of the motherboard. That adds layer count to your motherboard, increases the cost, but it's not that important because, you know, what's important on a GPU systems are the GPUs that are hanging out of these host motherboard, not the host motherboard itself. The host motherboard itself is important in a sense that it needs to be extremely reliable and it has the feature sets that you need to support the number of GPUs. Okay? So key thing here that I want you to take a look at are the arrangements of the 4 PCI Express slot. All of those slots we're routing by 16 lanes. Okay? When we design this motherboard, we know exactly what the trace lengths from each of the processors to those sockets are. Okay? And then we calculate how much distance we need to go out in order to support GPU endpoints to that. And then there's a lot of signal integrity studies that is done to ensure that we can drive PCI Express Gen 3 signal strength out to the end device. That's where a lot of the reliability comes in from the systems, by the way. Okay? So for some of you who have deployed fairly good size of GPU systems out there, probably have seen a lot of random PCI Express drop errors. You've seen PCI Express, what do you call it? When the cards drop off the bus, for instance, those are usually indications of loss of noise. Okay? Okay, lots of noise between the 2 devices, and the devices not being able to drive that high speed in a reliable fashion. So this kind of gives you a quick view. What we did was we did an analysis of each slot number 1, 2, 3, and 4. Okay? What the trace lengths on the main board was, what the material is, what the nominal impedance of that connector was. Take a look at the connector, and then we take a look at, okay, how much distance are the GPUs coming off of that PCI Express slot? What are the type of materials that we need to use? What are the type of, what is the signal integrity that we need to pay attention to in order to make sure that we can drive Gen 3 speeds on all of these systems? And on the right-hand side, you're seeing that total loss from the connector coming out of the motherboard down to our PCI Express device is still comfortably in range so that we can drive Gen 3 speeds. So we do a lot of these studies. We go out and do prototypes and whatnot. We measure it again to make sure that our assumptions are correct, and so that the bus is clean and that we can drive these GPUs the way that NVIDIA really intended to have these GPUs driven at. Okay? So we talked a little bit about the importance of signal integrity. We talked a little bit about the importance of cooling. Let's talk about serviceability as well, because sometimes these devices will fail and you need to service them. Or in certain cases, many of our customers like to upgrade their systems because the host on the GPU side, the host motherboard and the GPUs are on a different development cycle. Okay? So when NVIDIA comes out with a next generation GPU card, you really don't have to upgrade the host, for instance. You just want to upgrade the GPUs. So we wanted to give our customers the ability to be able to easily do that. So on our chassis, the GPU card cage is serviceable. And inside, there's 4 cartridge slots where the GPUs can go in. And if you want to be able to upgrade, let's say, a K40 GPU to a K80 GPU, you could leave everything the same. Only thing you need to change out are the cartridges. Okay? I talked a little bit about future-proofing our design. Okay? If you take a look at NVIDIA, starting from the Fermi cards, remember the M2090 cards, out to where we are today, there's been slight mechanical changes that have taken place. The cards have gotten a little longer. The connector locations have changed. The type of power connectors have changed, right? So what we wanted to do was, the yellow outline is the size of our GPU cartridge, okay? And the red represents the PCI Express Gen 3 standard size. What that means is that if NVIDIA wants to go out there, stay within the PCIe specifications, they can literally grow out that card up to that red size if they wanted to. Not saying that they're going to, but they could. And it'll still be within the specs. So with some of the other systems, if they design it to K40 and K80, you can't really upgrade them if NVIDIA decides they're going to move a connector here or grow out their card. But in our system, as you can see, we have more than enough room. Okay? Talk a little bit about cooling. So other than PCI Express signal integrity, the second thing that really dictates the performance of the GPUs is how cool you can maintain those GPUs. Okay? Well, reliable power is actually important too. Okay? You want to make sure that you're able to provide clean power to the GPUs. But other than PCI Express signal integrity, it's the cooling. So we work with some of our customers, and what we found out of doing massive deployments of GPUs is that if you can keep the GPUs operating at a little under 70 degrees Celsius, then overall performance and the reliability of GPUs stay very, very good. When you go beyond 70 degrees, we see a sharp increase, okay, in the reliability of the GPUs. So what we want to do is, the key number is 70. So what we did was, on our Storm system, we put 22 of these Storm system inside of a single rack, and this is the results of the worst one inside that rack. And as you can see, plenty of margins when we're driving these GPUs to its maximum performance. These were based on K40s. Okay? And this was measured at our Chippewa Falls manufacturing facility with about 27 C ambient temperature. Most data centers keep their data centers between about 22, 24 or so. DGEM was running so that we can really drive the GPUs hot.
The graphic, was it that there are different temperatures for each? Is the reporting value of the card?
Yes. So you can actually, through the SM bus, you can actually ping the GPU temperatures. And you probably noticed that the top 4 is slightly higher than the bottom 4. And the reason is because the way we lay out the GPUs, we have a GPU in the front and we have a shadow GPU in the back. So the rear GPU actually gets a little bit of elevated heat. But even then, as you can see, there's plenty of margins there. Yes?
Do you have any experiments where you looked at the impact of memory coalescing on the thermal rise? Because of all the misses, if you're tolerating latency through all the massive number of threads, or worse, did you look at what happens when you be really conscious of the memory, right? And then that way you don't have to switch warps as much, right? And what the thermal impact of that was.
Let me get back to you on that one. Okay? I'll be happy to address it maybe afterwards. I want to make sure that I give my colleague plenty of time for her talk as well. Okay? So I think this is my second to last slide. I told you that each of these servers, I think, take in about 3 kilowatts of power. So when you start putting it about 22 of these servers, that means one cabinet can consume about 66 kilowatts of heat. So how do you remove all that heat? Okay, so we actually work with our rear door heat exchanger partner and custom design a cooling door that can actually remove all of that heat. So this is actually a room-neutral design. What this means is that you can literally, as long as you got power in the data center, right, we're not going to impact your data center and make your data center facility guy pretty happy, okay? Okay, so the last slide that I have is, what good is all this hardware if you can't extract the necessary performance from these GPUs? So I think one of the things that NVIDIA has done really, really well, a fantastic job at, is that they not only made a fantastic hardware, but they invested a lot in having the tools so that you can extract the performance from that GPU. So where Cray has done, and not a lot of people know this, but Cray actually has more software engineers than hardware engineers, we've developed tools so that you can extract that performance out of these GPUs on a system like Storm where you have multiple of these GPUs. And this is a stack that's delivered with all of our Cray CS Storm machines. Okay? So I'm going to pass it over to my partner, Maria, and now she's going to talk about how we use these platforms and the experiences that we've gained in trying to scale the application on these multi-GPU systems.
Thank you. Okay, so in this part, so let's see. I know I have to sit somewhere. How far away? Or maybe he needs to move. Okay. Is it good enough? I'm fine if I sit here. Okay. All right. So in this part of the talk, I was thinking the audience is pretty technical. So how many of you tuned this is a large system for HPL? Anybody? One. Okay. So I wanted to show you what we do most of the time when we want to understand the system performance. And you know, Cray is submitting lots of top 500s, and we need to understand the performance. Many of our RFPs require peak performance. So in this case, we need to understand how the systems behave. Yeah. And initially, when we built the system for K40, when K80 came out, it's like, OK, what do I know about it? And how do I even try to understand how much better or what do I need to know about the behavior of the system with K80 versus K40? So what do we know about K80 versus K40? So of course, NVIDIA data that we received. We looked at double the memory. We said, OK, the form factor is the same as K40, but they are really two ASICs inside the card. And really, each one of them is capped at 150 watts. It's not that the sum is 300. It's each one of them. What else do we like? We like that the memory is double. We've seen many customers that have applications that take advantage of the double the memory. They store data on the GPUs. We see also the double precision is actually really good. Maybe I should stay here. So the double precision is really good. And we have a lot of customers who do double precision calculations in oil and gas seismic, lots of single precision, sorry. And also, NVIDIA K80 has a really nice auto boost. So OK, we said, OK, fine, these are good. What do we not know? We looked at the graph on the bottom, and I say, OK, fine. I see most of our customers look at the double precision piece. So I say, what can I tell them? What do I expect at the system level? So I'm thinking probably the peak performance on a system with some applications will be between 30% and 70% better with K80. I'm also thinking I do not know how it really depends on how much communication between GPU and memory, GPU and CPU there will be, or between GPUs. And we really don't have a lot of experience with GPU direct RDMA. So, OK, I know that. How does that impact at the node level? So most of the time what we do, we actually want to study with boost, without boost. I have to say, in the past, when we did HPL on the system with the 8K40, we actually used no boost mode. Yeah? So we got the best HPL. Also in the green entry, the number 4 in the green 500 is actually with no boost. So OK, we know that on K40. We have to see if K80 is the same or not. So what do? We look at the K40 versus K80, a card, and then we run it at the node with the defaults. If you look here, there is a trick that all the performance people know. You always report the R peak is no boost, although you may run with boost on or auto boost. So the peak efficiency is actually pretty good. But we know that on the K40, we got better on the node level than 75%. So let's see, can we drive K80 turning off boost to a better number? And this sounds easy, but there is so much tuning on HPL in order to get this. Some of you shake their heads. So here's what we did. So no boost. a lot of fiddling to get the right clock speed, which to set all the GPUs. And we got around 80%. So we knew that K40 did around 80% for at a node level, and we got even better with K80. And what's nice here is that you see the numbers at the bottom, all around 30%. So at the card, 30% better, and at the system level, around 30% better, and in line with the peak and the peak on the GPU. So I'm happy with this. Lots of iterations. This, if you are not experienced, this will take weeks. If you are experienced, probably 2 weeks. If you are not experienced, a lot more. And then there was that little strangeness there between the peak with boost versus the Rmax or the system level. So I say, why is that? So 175%, so 75% better with K80. Probably if the application runs only on the GPU, maybe you get close to that. If you have any communication, probably, and HPL doesn't have that much communication, but still is not at 70% better. So, OK, we got this. Say, OK, at the node level, 80% is awesome. It's in line with what we've seen with the K40 storm. So let's look at the rack level. And since we had the results already that we submitted at the Green 500, so we already knew the K40 rack, how it does, 22 nodes per rack. So we scale up from a node to 4 nodes to 8 nodes. And so we are looking for HPL to be at some level to plateau, to not drop. And on the 22 server K40, back in October, we got around 69% efficiency with 22 nodes. And you can see the peak and the Rmax. With the K80, again, it takes a lot of fiddling, but we ended up with a similar number. And also, what I like most is that it stays around 30%. So we really wanted both the efficiency to be in line with the K40. So these are 8 GPU per node, 22 nodes in a rack. And these were really physically in a rack, cooled with the door, like John explained. And the 30% peak improvement, Rmax improvement. So I think, OK, we can use this tuned HPL at the system level. And the last thing, it makes a difference. We started, if you have the right HPL, so it was really easy to go from an HPL that we tuned for K40s to the K80 one. It was much harder the first time when you had the K40 storm system, because we started with the HPL that was tuned for the XC with K20 accelerators. And XC has 1 accelerator per CPU. So one on one, while here it's 4-to-1 GPUs per socket, right? OK, so some nice numbers. The peak performance, the number we got to K40. What do I expect at the system level with K80? So flops per square foot, probably 30% more. If you compare with regular blades, it's 6 times as many. It's quite impressive. It's the GPUs that help. And the power efficiency, flops per watt. Remember, we have that really nice number in Green 500. It's probably 14% better. Right now, it's just estimated. We haven't measured the power here. And our customer, who will announce soon that they got a system with the K80, I'll show you a picture of the system. We want them to announce that number. Yeah. So this is a really nice system if you have the right applications. And I guess all of you are here because you want to learn how to tune your apps for that many GPUs in a system. Let's look, what do we learn? How do you start? Given HPL, HPL is not something that will predict the application performance. But it'll give you a good feeling for what you expect. You know very well how HPL is supposed to behave. So if HPL does well, at least you have a check mark. Yes, I know how this behaves. If it runs really smoothly at the whole size of the system, probably my system is well balanced, it's well designed, I'm good, I can run applications on it. But every time, even on all acceptances, we are running HPL on our systems to make sure that they're smoothly growing to the largest size from a node in a couple of nodes and so. So let's see if I remember. You start at the node level, like John said. You run HPL and you look, temperature variation, power variation, clock speeds on the GPUs. say, okay, you run many, many hundreds of times HPL and say, okay, are we staying constant? Or are there any jumps? You understand how to set parameters for the HPL in order to run it at the large level. For each new system design, you have to do that. And then you expect HPL to kind of, efficiency to kind of plateau. So what happens when you have a large system, a brand new large system on the manufacturing floor? And it doesn't run very well at the very large size. So how do you start? You look at node-to-node communication. We are usually running DGEM, and then we run node-to-node communication. It's a lot of statistics, especially for the very large systems that we build. We study the test patterns. And so these are things I actually asked our performance team to tell me what they do. And they said the thing that is really helpful is that they have, our system management software has a GUI, so they can watch the system while running HPL, and they can see it in real life versus at the end of the job. So these are the things that they learned and told me. So at some point, they get experts at running HPL. Sometimes it's really out of the box, and sometimes it's not. So one example here. This 560 node system, the number 10 in top 500, we only had one night when we could run HPL. And if you look at the efficiency, it's not amazing because they had no time for tuning. But they done enough work on the 22 node that it came out number 10. I think if we had 3 days instead of overnight, it would have been much better. So, okay. So that's HPL. HPL gives you a sense of how well the system is built, if the interconnects work, if some GPUs are not connected correctly, that type of data. But that's not what the applications do. Now, we said, OK, fine. Can I find some applications that give me that 2x that I saw with K80? Is there anything out there? So we knew some of our customers store data on the GPU. So if it takes a while to put all the data, but once the data is there, they just do locally data crunching. So we were thinking, OK, K80s have twice as much the memory. Maybe in that type of application, we'll see a 2x. So we had a when we had the K, we have 2 nodes. Well, we have multiple nodes, but the ones that we can play all the time with, there are 2 nodes with K40, Storm with K40, and 2 nodes Storm with K80 in the benchmarking center. And we run this application that's an elastic wave propagation. And we started with an elastic media that has very uniform parameters, so like really one material, and then something with very complex geometry. So the white is really the linear scaling. The green is what we got with the simple model where the material was uniform. And the blue is when we put very, very complex geometry. So this was simulating an earthquake actually in Northern California. I have the size of the mesh if anybody is curious. But this one stores the data on the GPU. And this is strong scaling. We didn't increase the model size. We just divided it on the GPUs. So for that type, it worked really well. So it's not a lot of GPU to GPU communication. It's not a lot of communication to the memory. It's just run on the GPUs. So we were curious. That was K40. What do we get with K80? So first thing out of the box, and I have to say, these were all done by a colleague of mine, Kevin McMahon. And he gave me this number, and he's like, why is it 32 there? So we had 2 nodes. Well, of course, K80 reports 2 GPUs inside. So you look at the results, and you see run on 32 K80s. So once we start, I say, OK, fine. So it's linearly scaling if you increase the number of GPUs that you share your data over, you spread your data over. But that's not, I don't understand the node performance that way. I just know it linearly scales on the GPUs. So I said, OK, let's look at the number of GPU cards. So K40 is the red line, K80 is the blue line, and that's the time to completion of the job. So again, this is strong scaling, the same model. And then, OK, even simpler, if you want to look the full node, K40 versus K80. K80 completes, I don't know, 60% of the time faster, 60% faster. So it's almost that 2x. So this type of problem will give us really much better performance with K80 versus K40. We spoke with some of our oil and gas customers, and the ones who do seismic, they really store their data on the GPU. So we expect this is a good proxy for what they do. They need to test, but we're trying to see if we'll find something similar with what they are running on a regular basis. Another one. So this company was here, actually. So this is GIS Federal. What you see the graph is not the performance. What they do, they get the data from the web, like Twitter feeds, airline paths, traffic on the highway. And this is global information systems for people who need information about what's happening with traffic, what things are correlated. So in that case, really, how fast they run and how much richer the information they get depends on how much memory they have on the GPUs. So in this case, they told us, well, we want a system like yours. And they currently have systems with 2 GPUs. If we give them 8, they'll get 4 times more data on it. And this is K40. So of course, with K80, it will be twice as much. There are some applications that will get the 2x. Most of them that mostly are compute and not that much data storage, probably 1.3 to 1.7, that's what we expect. So, all right, we have some idea of how they will behave, and this is a list of interseason applications that I actually put together back in August when we launched the product. Say, okay, which applications and industries are appropriate? And what they put in green there, so since August, we have one customer, a couple of customers in each of those boxes already. So, and the system that I mentioned that we run on the 22 nodes with K80 is the one at the academic institution. And I'll show you some pictures. So in Chippewa Falls, we have a big manufacturing floor. I know some people who were there just a month ago. So this is the 560 node system in Chippewa Falls. We had the graphics artists who took out the people and the tiles on the floor, but that's a picture of the system with the doors that John spoke about. There are racks and racks of nodes. This is another system at the financial institution that we shipped in December. And this is the system that we shipped last week to a university here. And we won't steal their thunder, so we won't tell you how many nodes and what's the performance, but they will announce it soon. So that's picture last week and Friday from the manufacturing when they packed the system. You see the labels and all that. So we are really, really happy with the system. And I listened this morning to the presentation, the keynote speaker, and he was speaking about the rockets and the fuel. Any of you listen to that? So I was saying, we have the rocket. We had it for a while. We are just looking for the customers who have the fuel, right? The right data and the right applications. Kevin is the one who helped me a lot on our side, and the NVIDIA dev tech team, oh my God. We wrote so many notes to them to try to figure out what are good applications to run, try different things, HPL from Massimiliano, so really grateful to those. Thank you.